I'm happy to meet more people interested in this combination of AI safety and like the natural science of what even are neural networks, how do they work. I have a neuroscience background and therefore I'm interested in this very scientific aspect of how these things work, but of course it has consequences for AI safety. So the talk will have the following three parts. First, I will just mention about polysemanticity and why we should care from an AI safety perspective. Then I'll talk about monosemanticity in biological neural networks, and finally polysemanticity. Now I should mention, and I'm going to repeat this a lot, neuroscience is very broad. There's so many things I could talk about. I'm just selecting a few that I find interesting that I know about. Okay, first of all, what is polysemanticity and why should we, this audience, about AI safety, care? So first of all, just to define things, polysemanticity is the observation of a single neuron, and I define it in the following. So an individual neuron activates in response to more than one distinct feature. Okay, and you also ask about, well, what's a feature, what's distinct features, and also what counts as activation. Anyway, let's just keep it a little bit high level. You might have heard of this word called superposition, which is also related to polysemanticity, but not the same. So polysemanticity, I and others say, is a hypothesized cause of polysemanticity, and superposition occurs when the number of features in a neural network represents is greater than the number of neurons, and therefore the neural networks assign features to an overcomplete, and that's important, an overcomplete set of directions in the collective neural activation space. Okay, so this is what I'll be working with. These definitions. Does anyone have any questions at this point? It's kind of like fundamental to the talk. Okay.
So,
yeah.
Receptive field of a neuron.
The receptive field of a neuron. Yeah, you could say the receptive field of the neurons are, you know, those areas in the activation space where they become active, right? Yeah.
I have a question.
Oh, sorry. Yeah.
Is there a definition of what a feature means?
No. So why should this audience particularly care about it? Well, if you care about large language models and the implications, you'll know, or you'd like to know perhaps, that natural language embeddings are sparse linear combinations of elementary word factors. So here's some different words. For example, this string of the digits 2, 3, 23 actually is a linear combination of about 70% number as a factor, 30% roughly time, and actually, you know, those add up to 130 and 70, but actually there's a little bit, 1%, that is actually distinguishing 23 from all these other numbers that have a linear combination of both number and time. And you can see different words here. A large amount of their identity, you could say, is made up of these lower factors. And in all these plots, this this green color, I believe, is like the others category. So on the right, you've got different sort of factors. Anytime you see this teal greeny color, that's like an other thing. So that's like maybe some of the more unique identity or fingerprint of that particular node. Now, that that sort of shows that you can make different words from different factors underlying this. Many people might have heard of this model called a toy model superposition. And in this model, what they do is they have a certain number of features, and they're trying to have an auto-encoder reinterpret and reproduce these features. And you go through some number of neurons, but you, importantly, can add some sort of sparsity to the inputs. And if you add a certain amount of sparsity to the inputs, then not all the time do you need to reconstruct the whole signal, right? If you always have to reconstruct the whole signal, then it's sort of very difficult and impossible to, let's say with just 2 neurons in this case, map all possible types of features, in this case 5 different features, to distinct points, right? So what it does in this 0% sparsity case of the input features, you find that you just find 2 different directions in the neural activation space, X and Y being 2 different neurons, and you find that they just go to 2 separate points separated by a right angle. But if you have a lot of sparsity, like 80% sparsity, then they start creating these antipodal pairs. So in one direction is one neuron, one feature, another feature, and so on. The colors, by the way, are about importance, so that I'll just skip over this, but they are ordered by some importance, and the more important ones get pushed out of the origin first. And then finally, if you have enough sparsity, then these will sort of shift around such that you don't have just orthogonality nor antipodality, but you also have some kind of like instead of 90% angle, 90 degree angles, you have like 89 degrees or 91 in this. I don't know what it is, but we're in only 2 dimensions, so it tries to fit all of these in as best it can. But in higher dimensions, it's probably closer to orthogonal. Yeah.
How does it measure sparsity?
It's the number of features that are present in some sort of like random way. You sort of just randomly delete with some probability the amount of information that's there. I can't remember what
The number of features divided on the number of neurons?
No, it's the number of inputs that you have.
It's about the data distribution.
Yeah, it's the inputs. Yeah.
And can I ask like a more social question or something?
Uh-huh.
So when some neuroscientists were using sort of sparse coding for like some time before this work, or
Yes.
like, so what is, do you think that this like added a lot to your understanding or like to models for example? Or
Not
is it-
particularly.
Okay, so it's not pretty clear for neuroscientists.
Yeah.
It's all, okay, nice.
So, sorry, just to interpret this, is this saying that if your data is in sparse, you only care about the most important features?
Yeah, so if you want to do this auto-encoder thing where you try and fit more features into the neural space that you have neurons for, so you have more neurons, you have 5 features, 2 neurons. Try and shove them in. And in the case that you always have all these features present, then the best you can do is just pick the 2 most important ones. Then, if you have some more sparsity in these inputs, so only some of them occur some of the time, then you can afford to sort of distribute them in these following ways.
And how come they all have the same length?
I don't know. I guess it's probably just to do with like some normalization of the data and the way that it's outputted.
Yeah. When you compute the minima, it just works out.
Yeah. And so, this sort of idea of sparsity shows up in large language models and transformers. So in 2021, some people at Meta had this interesting paper where they had this matrix where they had different vectors which were sort of sparse features that they were trying to decode from different activations in the residual stream, what we call, and try to encode using those some sort of sparse inference of features. And when you do that, for example, on text, you find an example on the right. This is different text tokens which are being